All right, hello everyone and welcome to the nitration lab for organic chemistry. So in this lab, we're going to be covering a nitration reaction, and a nitration reaction is a special type of electrophilic aromatic substitution, or EAS reaction. So you may have heard of these reactions covered in your lecture, but we're going to do a little bit of a refresher session on EAS reactions. So what is an EAS reaction? An EAS reaction is a reaction where a hydrogen ion, or a hydrogen on a benzene ring, or it could be another aromatic compound, is replaced with an electrophile, which we call E in a general sense. So if we were to depict this in a reaction scheme, we have some sort of ring. It's normally benzene, though it could be another aromatic compound. Okay. So this is going to act as our nucleophile. Okay, and this ring is going to attack an electrophilic reagent. So this is our reagent. And this first step here is called addition. So this electrophile is going to be added to the benzene ring. Okay, in doing so, it forms this special carbocation intermediate. So here's our electrophile. I've added it to this carbon here. And in doing so, we now have a carbocation intermediate, which we sometimes refer to as an arenium intermediate. And it's sometimes also referred to as a sigma complex. So that's the Greek letter for sigma. Okay? And this arenium intermediate is very unstable. So it reacts very rapidly in the second step. The second step is an elimination. So in our reaction mixture, a base with a lone pair of electrons is going to deprotonate that hydrogen and reform the double bond here to give us the product. So here's our product. And the overall transformation is from a hydrogen to an electrophile. So that's the substitution portion. Okay, and then this is our product. One thing to note here, the rate determining step, also called the slow step, is step 1 in an EAS. And the reason it's the slow step is because this step here has a very high activation energy barrier. And the reason the activation energy barrier is high is because this first step destroys the aromaticity of the ring. So the ring loses aromaticity. And aromaticity is a stabilizing factor. So to remove aromaticity is to make something very unstable. It requires a lot of energy to do. So this step proceeds quite slowly, but the second step proceeds quite quickly. Let's look at some of the influences that substituents have on EAS reactions. So if we have a benzene ring here with a substituent, so a substituent is anything other than hydrogen, what are the different positions on this ring in relation to this substituent? Well, the positions immediately next to it, or immediately adjacent to it, this position is referred to as the ortho position. Okay, the positions that are 2 carbons away, so 1, 2 carbons away, is referred to as the meta position. And then the carbon that is directly across, or 3 carbons away, 1, 2, 3 carbons away from the substituent, this is called the para position. And we can have different types of substituents on different types of positions. So just like in the Diels-Alder reaction, the 2 types of substituents are donating groups and withdrawing groups. So electron donating groups, electron withdrawing groups. And let's talk about how each of them influences the rate of these EAS reactions. So to remind ourselves, an electron donating group is an atom that normally contains a lone pair of electrons. Or it can be an alkyl group. So alkyl groups like methyl, ethyl, tert-butyl are very slightly electron donating. So those are also count as electron donating groups. Okay, electron withdrawing groups are atoms. So if the atom connected to the ring has a positive charge or a partial positive charge, delta positive. Okay, or it can be a halogen. So halogens like fluorine, chlorine, or bromine, so these atoms are strongly electronegative. They like to withdraw electron density, and they also count as electron withdrawing groups. Okay, and the purpose of these groups, or the effect these groups have, is they will either stabilize or destabilize the rhenium intermediate. So that rhenium complex that we talked about in the just previously will be affected. The stability of that ion will be affected by, depending on what group this, what substituent the ring contains. So for an electron donating group, if this substituent is donating, it's going to push electron density into the ring. So the ring is going to have increased electron density. Okay, in doing so, it turns it into a stronger nucleophile. Okay, so in an EAS reaction, benzene is acting as the nucleophile, and if we're pushing electron density into the ring, it makes it a stronger nucleophile, and hence it reacts faster. So electron donating groups are referred to as activating groups. So it reacts faster. So faster reaction. Conversely, an electron withdrawing group is going to decrease the electron density of the ring. And if you decrease the electron density of the ring, if you're pushing electron density outside of the ring is no longer a good nucleophile. It's now a weaker nucleophile. Therefore, we call these groups deactivating groups. And they have slower reactions in EAS. So what are some of the examples of these substituents? So for an electron donating group, we can have something like an ether, OR, maybe OH, NH2 is also common. And then you can have alkyl groups. So in this case, it's methyl, but it could be ethyl, tert-butyl, or something else. You can also have something interesting like an ester if it's connected at the oxygen atom. Okay, so that would count as an electron donating group because the oxygen has lone pairs. For electron withdrawing groups, obviously we have the halogens, so we can have something like chlorine, nitro, which is what we're adding to the ring for this experiment. You can have cyano, and then typically any carbonyl compound. So this carbonyl carbon has a slight delta positive, this nitrogen is positive, and then there's a slight partial positive on carbon in cyanide. So these are electron withdrawing groups. Okay, let's go into a little more detail about the exact specification of each and what they do on where the substituents are, or where it will direct substitution. So for an electron donating group, here we have a ring with an electron donating group, and we could potentially form 3 regioisomers. So the electrophile could add here, here, or here, and then generate some different types of these products. So if we're going to compare these, we need to analyze what the intermediate, the sigma intermediate, is going to look like after the electrophile adds, so after step 1. So let's look at the ortho substitution. So if we have a ring, so here's our benzene ring, and I'm going to draw it as the intermediate. And for an electron donating group, we're just going to choose OR. We're going to pretend it's an ether. Okay, and if you add the electrophile here, the positive charge will be right here. And this is very beneficial because the lone pairs on this oxygen can resonate down and actually stabilize this positive charge because it's right next to it. Okay, and you can see in the resonance structure that now the positive charge is on oxygen. So it has withdrawn the positive charge out of the ring. It's delocalized it. Okay, if we look at the para-substitution, we'll find that it's very similar. So here we have another sigma intermediate, but now the electrophile is added to the para position. Okay, and our carbocation is here. So it may not seem initially that we have a resonance structure that might work, but if we push electrons around, we can slowly move the positive charge towards the oxygen, which is our goal. Okay, so now with this resonance structure, we move this pi bond here, and now our pi bond is right here, right next to the oxygen, in which case it can stabilize the intermediate. Okay, so in these two instances, these resonance structures show that the positive charge is delocalized outside of the ring. And the consequence is that this is a more stable intermediate. It has a lower activation energy barrier. Now, meta, as you might have guessed, is going to, meta is going to be a little bit different. If we have a meta-substitution, so say the electrophile went there, okay, our carbocation will put here, and we're going to try to do the same exercise. We're going to try to get this positive charge to this carbon here so that it can be stabilized by the electron donating group. Okay, so the positive charge will be there. Oops, H. Okay, well, it's not there, so let's try again. We'll push this pi bond here. And as you can see, no matter how hard we try with these pi bonds, the positive charge is never delocalized outside of the ring. In other words, this electron donating group, the ether here, cannot stabilize this sigma intermediate when it's substituting at the meta position. So this is a less stable intermediate. Okay. So what can we conclude from this? We can conclude that electron donating groups are ortho-para directors. So because this is a more stable complex at the ortho and para substitution patterns, if your ring has an electron donating group, the likelihood is that the electrophile will add to the ortho or the para positions because they have more stable intermediates. Whereas the meta intermediate is unfavored because it does not benefit from resonance delocalization of the positive charge. Okay, let's look at the electron withdrawing group now. Okay, so I have the same setup here, electron withdrawing group, and we're going to do the same exercise. So this time, let's do ortho first, and our electron withdrawing group, I'm going to choose a carbonyl compound. Okay, and let's say we substitute on the ortho position, okay, giving us a positive charge here. Okay, in this case, we're going to look at how these electron withdrawing groups destabilize this intermediate. So if we draw a resonance structure where this pi bond between the oxygen and carbon becomes a lone pair, we'll get something that looks like this. Okay. And in this case, you can see that we have two positive charges that are on adjacent carbons, and this is very unstable. So this will actually increase the activation energy to form this intermediate. So that's a destabilizing factor. Para is a similar story. So if we have a para substitution, okay, and I'm going to draw the carbonyl as its resonance form, like that. Well, here's our carbocation. If we shift this pi bond here, we can see that indeed there will be two adjacent positive charges. Okay, and in this case, these are destabilizing factors. So adjacent positive charges, very unstable. Okay. So these form at a slower rate. If we look at a meta-substitution pattern, okay, so let's say the electrophile added to the meta-carbon, okay, and then here's our carbonyl. Okay, if we shift this pi bond here, the positive charge will now be on this carbon. Oops, I forgot a positive charge here. Okay, and we can push electrons that way. Oops, sorry, that's the that would be the reverse. Just going back there, we're going to push this pi bond here. Okay, so here's the new bond we form here. This pi bond is here, and then our electrophile is still there. This would be our positive charge here. I meant to put R here for the carbonyl compound. And as you can see, with the three resonance structures we've drawn, the positive charge is still in the ring, but it's never on this carbon. It's never adjacent here. So because of that, because the positive charges are never adjacent, this resonance structure, or this sigma intermediate, is said to be more stable compared to the ortho and para substituents. So it's not so much that the ring would prefer to do this in an EAS reaction, but it's more so that instead of these being meta-directors, it's more like they're ortho-para avoiders. They want to avoid these two intermediates because they're very unstable. And if it has to substitute, it prefers to do it on the meta position because that's the more stable of these three. Okay, so our conclusion here is that if you have an electron withdrawing group on your benzene ring, they're going to act as meta-directors. It's going to direct the electrophile to the meta position, and they're also deactivating, as we said before. So they make the ring less nucleophilic. It has a slower reaction, but if it does react at all, it will prefer to do it at the meta position. There's a little bit of an exception here. If we look at halogens, so halogens are special electron withdrawing groups, because while they are deactivating, they are not meta-directors. They're actually ortho-para directors. And that's because the halogen atoms themselves have lone pairs. And just like with the previous resonance structures for an electron donating group, the resonance structures you can draw show that the positive charge can be delocalized via the halogen. So they're actually ortho-para directors and not meta-directors like electron withdrawing groups. So let's talk about the specific reaction we're going to do. Okay, so the reaction we're performing is a nitration of this group. So methyl benzoate, you can see the hydrogen we're going to replace is right there, and we're going to exchange it for a nitro group. So it's called a nitration. Methyl benzoate, so this is an ester, that's the functional group, and it is an electron withdrawing group. Okay, so you might be able to draw a resonance structure where rings come out, or electrons come out of the ring and into the oxygen here. So because it's an electron withdrawing group, it's going to be directed the nitro group to the meta position. So you can see that this nitro has been added to the meta position here. Let's talk a little bit about the mechanism of how this occurs, how the nitrate or the nitro group is actually attached to the ring. So we're using two very strong acids, very concentrated acids, nitric acid and sulfuric acid. And very interestingly, they actually react with each other in an acid-base reaction. So you normally think about acids reacting with with bases, but in this case, it's an acid reacting with another acid. So if we have our nitric acid here, okay, what's going to happen is the sulfuric acid is actually going to protonate the nitric acid. Okay, so now our nitric acid is protonated. Okay, and now you can see we have water. We have H2O here, and that's now a good leaving group. So what can happen is electrons from the lone pair on this oxygen come down, and it kicks off water. Okay, and now what we form is our active electrophile. This is the electrophile that's going to be reacting. And this molecule here is called nitronium. Okay, so what will happen is in our reaction, we have our methyl benzoate. Okay, so here's our ester. Okay, this ring is going to attack the nitronium. It's going to attack the nitrogen. Okay, so this is the addition step, step 1 in EAS. Okay, so there's our nitro group. Here is the hydrogen. Okay, and then here's our carbocation right there. Then our ester is still there. And then finally a base, in this case it's the bisulfite or bisulfate anion that's going to come back and it's going to deprotonate that H and return the electrons to the ring. Okay, so we've restored our aromaticity and we have our product, our meta-nitromethyl benzoate. So we'll see that in the lab, but before we go to the lab, the last thing I wanted to touch on is we're going to discuss a little bit more about nitration. So nitration is not just used for one set of things. Nitration actually can be used to make explosives. So very interesting compound. Explosives. I think I misspelled that. Explosives. Okay. And these explosives have very names that you might recognize. So this molecule here on the left is called toluene. And if you perform an EAS on it, so remember, this is an alkyl group, so it's electron donating. It's an ortho para director, and you can see that it's directed the nitro groups to the ortho and para positions. So we've nitrated toluene with 3 of them. So if you were to name this molecule, you would call it trinitro toluene. And maybe you see the acronym, but this is TNT. So you've heard of TNT, maybe in Minecraft. If you have glycerin here, so this molecule is glycerin. Okay, if you nitrate glycerin, instead of a ring acting as a nucleophile, you have oxygens. So these oxygens will attack the nitronium ion, and you get this molecule here. So this one is nitroglycerin. Okay, and then here we have some cellulose. So cellulose is the plant fiber that we use for paper, for clothing, in cotton, very common. And if you nitrate cellulose, you get nitrocellulose, sometimes referred to as gun cotton, because it's used as a propellant in firearms. So very interesting. If you add nitrate to a molecule, or you add a NO2 group, you can get things to burn much better. So in a typical combustion reaction, you take an organic compound with carbon, and you mix it with oxygen, and then you get carbon dioxide and water. So if you can increase the amount of oxygen in your organic compound, you can make it more energetic. So by introducing a nitro group, we can introduce nitrogen and oxygen, and it makes these things burn or explode much better. So we're going to go to the lab, and we're going to show you the nitration of methyl benzoate. Okay, so we're going to start our experimental here. So this is our reaction apparatus here. We have an ice bath because the reaction needs to be kept cold. We have an Erlenmeyer flask with a thermometer to read the temperature. We have a stir bar in there, but you can't see it. This is our starting material, our methyl benzoate. So methyl benzoate is a liquid, colorless liquid, so keep that in mind. And then here we have on ice some nitration mixture. So there are 4 mils of nitric acid in here, and it's mixed with a little bit of sulfuric acid. And then we have our solvent, which is sulfuric acid. So the solvent for this reaction is actually sulfuric acid. And they both need to be kept cold. So to do the reaction, it's very simple. You just take your sulfuric acid. We're going to add it all to our reaction flask. By the way, this sulfuric acid is very corrosive. So I'll take a piece of paper from our thing here. So it's very important you don't get these chemicals on you, the acids, because they can quite readily dehydrate your skin. So if we put a little bit of sulfuric acid on the paper, you can see immediately it dehydrates the paper. Okay? And it gets quite warm doing that. So you can see it's gotten on my glove a little bit here. I'm going to change my glove and be right back. Okay, so changed my glove. We're all good. Now we're going to take our starting material, our methyl benzoate, and we're just going to put it into our reaction flask. So okay, so that's all of it there. So now what we're going to do is we're going to turn on the stirring, and we're going to check the temperature. So let's see. So right now we're at, oh, very good. We're right at 14 degrees Celsius, okay? Which is right where we want to be. So this reaction, we want to keep it below 15 degrees Celsius. And the reason is if it exceeds 15 degrees Celsius, you start to form other side products like the ortho para isomers. If you give enough energy, it'll form the less stable products. So we want the meta product. So we want to keep this reaction cold, below 15 Celsius. And the way that works is we're going to add the nitration mixture. So this is the electrophile. Our nitronium is in here. And we're going to add it dropwise as quickly as possible, but at the same time keeping it below 15 C. So we're going to increase the stirring a little bit, and we're going to begin addition. So if the temperature doesn't exceed 15, I'll add more. But if it starts to exceed 15, I'll stop adding. So here we go. You can see how quickly the temperature increases as I add the nitration mixture. So gotta be careful not to overshoot. Okay, so I believe, yep, we've added all of our nitration mixture. And for the most part, we have been able to keep it under 15 C. So right now it's at about 10 or 11. Okay, so now that all the nitration mixture has been added, we're going to let this mixture stir for about 15 minutes. And then we're going to precipitate the product from it. So right now everything's soluble in sulfuric acid. So we'll mix it with some water, precipitate the product, which is a solid, and then isolate it, dry it, and then get a mass. Okay, all right, so we've allowed it to come up to room temperature. The temperature is now about 15, 17 C, and it's been stirring for about 15 minutes. So the reaction should be complete. Okay, as you can see, it's still all pretty much homogeneous. There's a little bit of air bubbles because it was stirring so vigorously. So what we're going to do is we're going to take this mixture and pour it onto crushed ice. So the reason we put it onto ice is because the sulfuric acid in here is exothermic when it mixes with water, so the ice helps keep the temperature very low. So there you go. And then we'll use a little bit of water to rinse out the Erlenmeyer flask. And there you can see some of the product precipitating as a white solid. So that's what we're after. And as you can see, it's also fuming because of the nitric acid. Okay, so should be sufficient. Now we're just going to stir it up. Okay, so now I think what we'll do is we'll put this and let it stir until all the ice is melted. And once all the ice is melted, we'll vacuum filter it and collect the product. Okay, so we have our mixture here. All the ice is melted, so now we're just going to collect the solids using vacuum filtration. So we have some solids on the filter, quite a bit actually. So we started with a lot of material, right? 6.8 grams, so we're expecting quite a bit. But there is quite a bit of acid, so the filtrate here is extremely acidic, which also means that these solids are probably still have some acid in them. So we need to wash them copiously with excess water to try to get as much of that acid out as possible. So add water. So we've got our solid here, which has been drying on the filter for a little bit. Now we're going to try to get it out. So it's a nice fluffy off-white powder. So hopefully we'll get a big yield here. That part's a little pasty. That's okay. Okay, so we can just take that. We're going to transfer it to a scintillation vial here. Okay, we still got a little bit more. Okay, so I think that's sufficient. Just coax the little beer particles onto the paper. Okay. Okay, so quite a bit of product there. So it almost fills up a scintillation vial to the top. This is fairly heavy right now. I can even feel it right now, and that's probably because there's a lot of water in here. So as usual, we're going to place this in a vacuum desiccator, try to get all the water out, and then we'll get an accurate mass. Okay, so our product is dry. It's been in the vacuum desiccator for a few hours. We placed it on the balance, and the amount of product we have is 8.51 grams. Okay, so you can use that value, 8.51 grams, to calculate the percent yield for this reaction.